consumption disease, C-O-N-S-U-M-P-T, consumption disease, or the wasting away disease, because the individuals who are infected with tuberculosis, they often tend to lose weight over the course of time. The agent is a slow-growing pathogen, and one of the reasons why the agent is a slow-growing pathogen is because of the mycolic acid in the cell wall. The mycolic acid in the cell wall its synthesis is very prolonged. So there are too many steps for the synthesis of mycolic acid, and that makes the cell very slow growth. It has an extended generation time, and we talked about it a little bit earlier, and then again this is going to come up. Why the treatment? Because it has a slower generation time. The treatment options are also extended for several years to months together. Okay? The cell wall is made up of the mycolic acid, and that contributes to its inherent antibacterial resistance. The bacteria is very resistant to many of the antibacterial agents because the mycolic acid is impermeable to many of the aqueous antibacterial agents. So aqueous antibacterial agents, they cannot go inside, and that's one of the reasons is because of the mycolic acid, so it is inherently resistant to many of the aqueous antibacterial agents. So patients who are tuberculosis infected, their utensils and all, they need to be cleaned using a little bit more robust and some of the stronger antibacterial agents they need to be cleaned.
So it says antimicrobial resistance. Is that just a typo or is that something different?
Contributes to inherent antimicrobial resistance. The inbuilt antimicrobial resistance is because of the mycolic acid, which is vaccine. It prevents the entry of many of the aqueous antibacterial agents.
Okay.
Oftentimes, the host is unaware of the infection. They will slowly tend to lose weight, and depending upon the severity of the disease, host is unaware of the infection by the Mycobacterium tuberculosis, and oftentimes the resistance of the host is influenced by the presence of other illnesses. If they have like diabetes or immunocompromised condition, HIV or pneumonia, then they are much more susceptible. It comes with a vengeance in those individuals. And this is one of the opportunistic infection of HIV/AIDS patients as well as the immunocompromised individuals. People who are immunocompromised because they are undergoing radiation therapy, chemotherapy and all, they are also prone to getting tuberculosis. So the resistance, one of the factors that determines is the presence of other illness. If you just have the tuberculosis and no other collateral illnesses, possibly your immune system will try to take care of you. Physical or environmental factor also influences that, the resistance, because if the person is in a moist, damp environment for most of the time, it's going to exaggerate the tuberculosis. No light, moist, damp environment, that would make the situation go worse, and it would exaggerate the condition. And that's why earlier times, people who had tuberculosis, guess where they were being taken and housed? In Hawaii, or in Colorado. So we have some of the tuberculosis places in Hawaii and as well as the Colorado mountain, just because there they will be aware, there they will get clean air as well as bright, sunny, clean air. That's one of the ways by which you can try to recover the patients back to its normal day-to-day life. Overcrowding and malnutrition is another contributing factor. When I say overcrowding and malnutrition, that's one of the reasons why because of the malnutrition is very prevalent in many of the poor parts of the globe. That's one of the reasons like 9 million new cases of tuberculosis are detected and reported every year. That's a staggering number. And in US, in developed countries, also this has come up again, a new thing, so we have to reinvent the cycle because earlier times we had this, we got rid of it, and because of the increased incidence of HIV and AIDS, this disease is not just a disease of poor nations. It's a disease which spreads all across the globe, whether it is the poor nations or rich nations, everywhere it spreads. In developed parts of the world, it's because of an increased incidence of HIV and AIDS. In some of the other areas, it's because of the overcrowding and malnutrition. And overcrowding, what happens if one person has a tuberculosis, it's transmitted as aerosolized particles. So if one family member has it, more than likely it's going to be spread amongst different family members, and that's the reason also it continues in the family. Got it, folks? And obviously, if you're malnourished, the disease becomes worse in such instances. Individual stress, alcohol consumption, smoking, and drug abuse, they're another contributing factor. They're a second layer of contributing factors when you have individual stress. If you're stressed, you may look apparently very healthy, but then you open the floodgates to tuberculosis. And it's not just tuberculosis. When you are stressed, and I'm sure, during exam time, a lot of people, what you'll see suddenly, you will see them getting cold sores of the herpes outbreak. And that's because when you are stressed, the corticosteroids which are released, some of the corticosteroids, what they do is they depress the immune system. So your immune system gets lowered, and suddenly then you will be prone to getting tuberculosis, as well as in the case of the herpes infection, because that glucocorticoid has some other function that would cause the sudden reactivation of latent herpes. Okay, so those are some of the things, like when you are stressed, some of the corticosteroids which are released, that is one of the factors which would depress your immune system, and then you will be likely to get tuberculosis. Some of the organs that are affected, most likely people think that tuberculosis is exclusively a lung infection. But that's not the case. In tuberculosis, primarily it is a disease of lungs, so you have the pulmonary tuberculosis is much more common, but sometimes the bacteria can slip out from the lungs. It can go to different areas of the body, and that's what is called as extrapulmonary tuberculosis. And that time it could be either in the bones, in the meninges, or in the lymphatic system. The bacteria can go and it can colonize to cause the bone tuberculosis, the meningeal or the brain tuberculosis, or some of those lymphatic tuberculosis. So it is not exclusive. The take home here is it is not exclusive to the lungs to cause pulmonary tuberculosis, but it can be disseminated and it can go to other places of the body as well. There is also the different stages. There's a primary tuberculosis when it is confined within the lungs, and I'm going to catch up on this part a lot more in detail. Then there is a reactivated or the secondary tuberculosis. There's latent tuberculosis, and there's also what is called as a disseminated tuberculosis when it is distributed throughout your body in specific areas. So these are some of the organs that are affected, the different forms of the tuberculosis bacteria. Somebody can harbor latent tuberculosis for an extended period of time. which is there in your body. It's not causing any harm, it's not dividing, but it is just present in your body, and your immune system is keeping us a good tap on it. He's here. Now, this picture shows the pathogenesis. What happens with the tuberculosis bacteria? How does it really cause the disease? What happens? The bacteria, typically from an infected person, when the person basically coughs, or the person, yells, coughs, or anything of those activities, it will release the aerosolized particles from the lungs. So some of the aerosolized particle will be released, and typically some of the other unsuspecting individual will inhale those tuberculosis bacteria. And once they inhale via the respiratory droplets or the aerosolized particle from an infected person, the bacteria tends to be sucked into the alveoli of the lungs. So it goes to the alveoli of the lungs, and within the lungs alveoli, there are some of the phagocytes which are called as the alveolar macrophages. So the bacteria goes and targets those alveolar macrophages, which are sort of a defense component present in your lungs, in the alveoli of the lungs. Okay. Now, once the bacteria is recognized by the alveolar macrophages, it will be picked up, and they will try to kill the bacteria and try to inactivate the bacteria, because the bacteria will be picked up by the phagocytic process, and then the phagocytic vesicle will go and try to fuse with the lysosomes. But it is picked up, and the bacteria, when it is trying to go and fuse with the lysosome, I think I checked it out yesterday also, am I correct? Once it is in the phagocytic vesicle, that phagocytic vesicle is driven towards the lysosomes, because the lysosome has all the digestive enzymes, and that would kill the ingested microbes. Do you recall it, folks? Mm-hmm. Okay, so here also the same thing happens. The bacterium, what it does, it tries to inhibit the fusion between the lysosome and the phagocytic vesicle by which it came inside those macrophages. So it infects those macrophages, and over the course of time, the bacteria multiplies within this macrophages. So there is a cyclical event occurs. The bacteria, it multiplies within the macrophages, and then those are released from those infected macrophages to reinfect some of the neighboring new macrophages. So there's a continuous cycle going on there in the macrophages. And when this continues up until the time when the infected macrophages, it tends to secrete some of those cytokine type of stuff to attract some of the T cells near the infection site. So the macrophages will then secrete some of the cytokines to attract some of the T lymphocytes, and those T lymphocytes eventually will make more secretion of some of the other compound to get a backup of more macrophages. You see that? So it's something like, if there's a crime scene, the police are trying to investigate, or the public is there, then the police is going to call some of the backup police force. So here, the macrophages will basically, the macrophages will stimulate some of the T cell to be attracted to that area. And then the T cell will secrete some of the other cytokine to get more additional backup macrophages to control and to contain the infection. In the process, what happens there is the new macrophages which is coming, it will form a kind of a densely packed layer around the area where the dead macrophages as well as the infected macrophages are present. You form a sort of a perimeter around it by some of the closed and very, very close, as well as very, tightly packed cells. When that happens, over the course of time, some of the fibroblasts will also come around, and it will deposit the collagen layer. So typical of the inflammation process. So with that deposit of the fibrin or the collagen fibers, as well as the macrophages, which is forming a tight layer around the infected cell, that's what is called as tubercle. And the name tuberculosis is coming from the tubercles word, because tubercles is the one that will form a tight and a kind of an opaque structure. If you check it under the an X-ray of the lungs, it will show as opaque structures. So then, after a while, because those cells have nowhere to go, you will see if this tubercle will transform into what is called as a caseous necrosis. The bacteria with the ingested, the macrophages with the ingested bacteria, those macrophages will die, the cell will die, releasing the bacteria, and there will be some localized inflammation, and that's why you have this caseous necrosis, which forms a cheesy consistency with the dead cells. The dead macrophages, as well as some of the dead cells, which are all confined within this tuberculosis, within this, the tubercles, and that's what is called as a caseous necrosis. It has this cheesy consistency with the dead cells. With the dead cells, some of those, cells protein, some of the cellular fat, which are all released, they all get together and they form the kind of a cheesy consistency called as caseous necrosis. Okay. And now, when this is formed, there is a kind of a deadlock between the body's defense system and the bacteria which are present within that tubercles and the caseous necrosis. You reach a stalemate, a deadlock between those two, between the body's defense system and the bacteria that is infected. Over the course of time, the vesicle, this will rupture, and once it is ruptured, the new bacterial cells are all released, and they may be carried over to different areas of the body to initiate a second round of infection. And that's what is called as a secondary tuberculosis, when the bacterial cell breaks. So this whole thing gets ruptured, and when it breaks that deadlock or the stalemate, and ruptures the tubercles and reestablishes an inactive infection. That is what is called as a secondary tuberculosis. Secondary tuberculosis is much more commonly observed in some of the immunocompromised individuals. If you are healthy, then your bacteria will be confined within this area, within this caseous necrosis tubercles, it will be confined there only. But if you get immunocompromised, this is going to rupture, the bacterial cells are released, and those bacterial cells may be carried to different areas. It could be the spleen, and some of the other areas, it may be carried over to reestablish an infection foci. One second, you have a question?
So I actually had latent tuberculosis. Where in this whole thing did that
The
stop?
latent tuberculosis is over here, and a kind of is over here.
Okay. And then, so the medicine that they give you prevents this step from happening?
It doesn't prevent, it just keeps it all in a kind of locked state. And I'm going to talk about those medications also right now. Yes?
And like, for example, her situation, due to the fact that she's healthy, she didn't get the rupture.
No, she's healthy, and her immune system, she has a healthy immune system, so that's keeping a tab on this one perfectly fine.
So a healthy individual will not get the rupture?
No, it's ruptured one is only what happens if you are malnourished, if you are immunocompromised, if you are malnourished, if you are stressed out. Basically, if you are screwed, then you get it.
Clear TB without taking antibiotics, right?
Huh?
Even if you're super healthy, you can't clear TB without taking an antibiotic.
I'll talk about it.
Oh.
I'll talk. Is that clear, folks? Then you also have what is called as a disseminated tuberculosis. So disseminated tuberculosis, when the cells which are released from the ruptured tubercles, they're carried inside the macrophages by a blood and lymph to other sites of the body. And the other side could be the bone marrow, kidneys, spleen, the central nervous system to cause meningeal tuberculosis or the spleen tuberculosis. The bone, here's a bone marrow, then it causes what is called as a bone tuberculosis. So those are some of those, or these are some of the areas where the disseminated tuberculosis will go and will establish itself. What are the virulence factors? The first and the foremost virulence factor is, can you tell me some of the virulence factor, Flo? It is the slow growth and the longer generation time. So one is the slow growth with long generation time. And tell me one more. Anyone?
The ability to reproduce in the macrophage?
Huh?
Ability to reproduce in the macrophage?
There's its ability to multiply within the macrophage. I will buy that. Okay? So ability to multiply intracellularly. Oh boy, then I would say the third one. Yes?
We talked about in lab the growth factor.
There you go. I'm so impressed. You made my day. Okay, we made my evening. The third is the cord factor. Remember the cord factor? And that keeps the cells all clumped together. And when it is all clumped together and stays in a parallel alignment, it acts as an inhibitor for for the neutrophils to come and grab the bacteria. Or neutrophil, so this one inhibits clearance by the neutrophils.
Were you saying that basically they just can't grab once and they're stuck together?
It's all stuck together. They are all, the cord factor is one of the secreted protein that keeps all the cells in a parallel alignment, and when the neutrophil comes to clean it up, it fails to do that. The macrophages are screwed up, so the neutrophils, backup neutrophils try to come in and leave it. But they can't just phagocytose the bacteria because of the cord factor. Can you tell me one more for us? Huh? The ability, but that's the one, that's why it is able to multiply intracellularly by preventing the lysosome and the phagocytic fusion. Fourth one. Anybody, folks? It's very simple. You want me to write?
Yeah.
Can you tell me one more? See, you made my evening, so you make my night also. I'm like, tell me one more.
Oh, is it the
ability to retain water,
Huh?
the ability to, yeah.
Resistance to dehydration, resistance to dehydration or desiccation. And remember, folks, the cord factor becomes toxic to our body. The cord factor, which is secreted by the bacteria, is toxic to our body cells, but they do inhibit the clearance by the neutrophils. So these are some of the virulence factors which amplifies the disease-causing ability by this bacteria. You get it? Is that clear to everyone? So these are some of those. Now, the diagnosis. How about the diagnosis? How the tuberculosis is diagnosed? What are the treatment options for the tuberculosis bacteria? And at the same time, what is, you might have heard about MDR and XMDR, or extreme drug resistance tuberculosis bacteria. Have you heard about those things? People who work in the clinical facility, they might be aware of all of this. And I'm sure that if you work in the clinic, where's Andrea? Am I correct? You have to get this thing, that EPD, every year?
Oh, yeah.
Mm-hmm.
You know why? What does that mean?
To see if you're infected, right? Yeah. They put some of that into our body, and if we have a reaction to it, that means that we're positive, right?
That means?
That we're positive.
What does that mean if you're positive?
Means you've been exposed.
Yeah.
You're being exposed.
You also have to do that if you work in education.
Oh yeah, you are very right. And it always reminds me, I need to get my PPD done, because I
they
got
do
it
it
done
here
when
for
I was
free.
hired, and then it has to be done after not every year.
It's like every 2 or 3.
Huh?
It's like every 2
Every 2 or 3. If you're working with the children, it is something like that. They are much more stricter. In college, they are a little bit lenient, and I'm more taking it easy.
Professor, are you more at risk if you travel outside of the country?
I'll tell you. I'm going to get on. So the diagnosis is usually done by multi-drug therapy, and it's a long treatment. So the diagnosis is done by multi-drug therapy. What they do is, they oftentimes, patients are given a cocktail of drugs, and those cocktail of drugs include rifamycin. It includes rifamycin. It includes isoniazid, and it includes ethambutol. Isoniazid is the trademark name. This is the trademark name of isonicotinic acid. So isoniazid, rifamycin or rifampin, as well as the ethambutol are the 3 drugs given in combination. This is still one of the traditional way they do it, although after 40 years, they just came up with a new drug for tuberculosis, bedaquiline, and I'm going to catch up on that part in a second. But what these 2 drugs does, it inhibits mycolic acid synthesis. These 2 drugs inhibit the mycolic acid synthesis. And can you tell me what is the action of rifamycin, folks, if you recall? Anybody recall the action of rifamycin? What does it do?
Stops protein.
How?
The RNA transcriptase.
The RNA, the RNA polymerase. It blocks the action of RNA polymerase, and then it stops the protein synthesis. Why the rifamycin is effective against tuberculosis bacteria? Does anybody recall that part? Yes.
Because it grows so slowly?
In the turnover rate of the protein is slower because it's a slow-growing bacteria. Okay, so this one, it targets, the rifamycin targets the RNA polymerase. It targets RNA polymerase, and the turnover rate of the RNA polymerase is much slower, and that's the reason why the RNA polymerase is affected in the case of tuberculosis, but not in the case of E. coli, because E. coli has a rapid turnover rate. After 40 years of research and all the thing, we have just come up with a new drug called as beta-quilin, Q-U-I-L-I-N. Sorry. Beta-quilin, Q-I-L. Beta-quilin is one of those anti-tuberculosis drugs which has come after about 40 years later before we had some of those traditional drugs. What the beta-quilin drug does, it inhibits the ATP synthesis of the tuberculosis bacteria. It inhibits ATP synthesis of TB bacteria.
Are you able to take that one alone, or is it still the other?
You know
combined
what?
with
To
the
be
top?
honest, you have to still take the other one, but this was going to clear up the tuberculosis a little bit faster because it inhibits the ATP synthesis or ATP synthesis, and once it inhibits the ATP synthesis, the ATP supply will be cut off, and eventually the bacteria, because you know without the ATP, the cell will not be able to survive for long. And this is mainly given to individuals. Oftentimes, this beta-quilin is reserved for individual or is given to individual which is restricted for individuals who are ex-MDR or MDRs. People who are multi-drug resistance or the extreme multi-drug resistance, they are given beta-quilin because you don't want the resistant strains to develop against beta-quilin. MDR stands for MDR, it stands for multiple drug resistance or multiple. Oh, can I just finish? How much is there? No, it's going to take me some time. Can I just finish up this little bit on this one and then you take a break? Is that okay, Paul? Are you bored? Oh, you are? Okay. So this is called as a multiple drug resistance. Multiple drug resistance. And when public health officials use the word multiple drug resistant, it simply implies that the bacteria is resistant to the INH or the isoniazid and the rifamycin. If the bacteria are resistant to these two drugs, then those are referred to as MDR, resistant towards INH, isoniazid, and rifamycin. So if the bacteria can grow in the presence of these two drugs, then they are referred by the public health department as multi-drug resistant bacteria. The extreme multi-drug resistant bacteria is when they are resistant to these two, and in addition, 3 or 4 other antibacterial agents, then it is called as extreme multi-drug resistance. So, XMDR is the extreme when it is resistant for the above agents plus 3 or 4 other anti-tuberculosis drugs. In vitro. So what they do is they take the bacteria, they try to cultivate it, and then they try to see if the bacteria are resistant to not only those 2 classical anti-tuberculosis drugs, but again, in addition to that, they are resistant to 3 or 4 other anti-tuberculosis drugs. Then it is classified as an extreme multi-drug resistance. And I'm sure you might have heard about extreme MDR. Off and on, you come across extreme MDR, and such individuals need to be quarantined or they need to be isolated by the public health department. Is that clear, folks? You want to take a little break now? So for this one, we talked about the MDR and the XMDR. And by the way, for the bedaquiline, what we talked about, the new drug bedaquiline, that was FDA approved in 2014. Not too long back, it was first approved by FDA to be used on tuberculosis patients in 2013. And it is only reserved for the MDR and the XMDR because it's not given if you have the regular tuberculosis. You have to initially start with some of those routine anti-tuberculosis drugs in the top.
And is that because of expense, or is it because of expense, or some other reason?
No, it's because you don't want to develop a resistant strain toward the okay. What they also do, and let me do it now only, folks, this is a little bit off track, but still they use it in tuberculosis. There's another drug, what they use it for the Mycobacterium leprae, that is called as clofazimine.
I can Google for you.
Clofazimine.
Z. Clofazimine.
Clofazimine.
Yeah.
Clofazimine.
Yeah. You got it.
Clofazimine, what it does, it binds to the DNA. It binds to DNA of the Mycobacterium leprae. But then this is also used, now the clofazimine, that's right. Clofazimine is also used for the tuberculosis, for the treatment of tuberculosis. But primarily it is used to bind to the DNA of Mycobacterium leprae, but is also used as anti-tuberculosis drugs. Clofazimine.
And works the same way, like binding to the DNA.
It just binds to the DNA of Mycobacterium leprae, but it works in the same way in the case of the Mycobacterium tuberculosis. So this is also used. Now the next one is a tuberculin test. This is what is a tuberculin test. They use, do you know what do they inject in this one?
Purified protein derivative.
Good job. That's what is PPD. PPD stands for the purified protein derivative, and this is one of the cell wall protein. It's one of the proteins which is isolated from the cell wall of the mycobacterium. This PPD is injected subcutaneously. You don't have to do it all the way down. It's just below the skin surface. It is injected, and then it is observed after some time. If you exceed to observe it beyond 72 hours, it may give you a false result. It has to be observed by a medical worker within the span of 24 to 72 hours.
It's actually
48.
48 to 7, huh?
48.
48.
Oh, yes.
It can't be 24, yeah, not 24.
48 to 72 hours, sure, sorry.
What is in the quantum serum test, what are they testing for in the blood?
That is again a little bit different in the quantum test. What I believe is they look for some of the antibodies in their resistance. Okay. Okay, now PPD, so you know what is a PPD. What they do is they inject it subcutaneously, and then I can talk about the hypersensitivity reaction. It's one of those type 4 hypersensitivity reaction occurs. So if you have been exposed previously to tuberculosis, or if you have been vaccinated against tuberculosis, you will always test positive for the PPD, or the tuberculosis test. That's one of the reasons why most Asian folks, they may not have an active tuberculosis, but they will always test positive for the tuberculin test. They invariably will test positive for the tuberculin test. That does not mean there's active tuberculosis. It simply implies you have been exposed to the tuberculosis bacteria in the past, and you have some of those memory B cells, and the memory T cells are there in your body. And when they recognize this PPD, those memory B and the T cell is swing into action to cause a hypersensitivity reaction like this. All right? Now, the diagnosis is mainly confirmed by doing a sputum culture. During the sputum culture, and also you look for the chest X-ray. If you see the presence of tubercles, then that confirms the presence of the tuberculosis infection. So when you do the sputum test, you will do an acid-fast testing and look for tuberculosis bacteria. If the test result, if the acid-fast staining comes up as an acid-fast, then it confirms the presence of tuberculosis. And then possibly the doctor may ask you to take some of the anti-tuberculosis drugs sometimes. So this is how the tuberculosis is detected. This is how it is diagnosed. Prevention is mainly done. In this country, we don't do a vaccination against tuberculosis, but in some other places, there is a vaccine, mainly by the BCG vaccine. BCG stands for Bacillus of Calmette and Guerin, G-U-E-R-I. Bacillus of Calmette and Guerin, and these were the two French bacteriologists. What they did was they took the tuberculosis bacteria from the cattle, and then they attenuated those mycobacterium from the cattle. So this is an attenuated BCG, is the attenuated Mycobacterium bovis from cattle. When I say it has been attenuated strain, it simply means it has lost its ability to cause the disease, but it can stimulate the immune system and create the B cell and the T cells, the memory B cell and the T cell. But it would not cause a full-blown disease. That's what you mean by attenuated. It has lost the ability, it has lost the ability, or lost its virulence. It has lost its and oftentimes the vaccine against tuberculosis is reserved not for the general population, because general population is not given BCG vaccine, but it is reserved for individuals who work in the healthcare industry, specifically for people who are dealing with tuberculosis patients. Tuberculosis patients, healthcare workers, they are given the vaccine of BCG. It's not a preventive strategy. Remember, it's not a preventive, it's not a treatment option, but it's just a preventive strategy. If you're vaccinated, then you feed the memory B cell and the T cell, which will prevent from getting the infection.
So if you were infected before, would you get that vaccine as a prevention?
If you have been infected before, if you had an active infection and then you recover, that means your body immune system has already made the memory B cell and the T cell. Then this vaccine is not going to help you in anything. Oftentimes they give the vaccine depending upon your condition, because it may boost your immune system a little bit. Just like when you take those, what do you call it, a booster dose. So it may do it a little bit, even uplift the defense system of the body. Is that cool? Now the last one in this is, why do we use new anti-tuberculosis drugs? There is a big time push. There's a big time push in the healthcare industry to get some more anti-tuberculosis drugs, because it needs to be shorter and simpler, but again, it needs to be shorter and simpler, but again, it should be economically viable, and at the same time, multi-drug regimen for drug-sensitive tuberculosis. You have to take a cocktail of anti-tuberculosis drugs for people who are sensitive to tuberculosis. Shorter, more effective, and less toxic, less expensive regimen for drug-resistant tuberculosis patients. So shorter time, more effective, less toxic, as well as less expensive regimens for people who have a resistant tuberculosis infection. Yet at the same time, short, simple, easy tolerable, and safe regimens for latent tuberculosis. And last but not the least, drug with few of the drug-drug interaction. If you're taking tuberculosis drugs, and if you take a Tylenol along with it, you should not blow up your brain, or you should not shed it to pieces, so that's a drug-drug interaction. They can be safely provided for people who have HIV, because this is a big-time issue with the HIV, and that's why it is one of the deadly re-emerging infectious diseases. You have to reinvent the wheel for the control or the treatment of tuberculosis in all developed parts of the world. Before I get onto this one, folks, there's one thing which, because one of the reasons why drug-resistant strains of bacteria develop is because they stop taking the drug. Person who is infected with tuberculosis, I think I did mention it last time also, you have to take those anti-tuberculosis drugs for a long period of time. And oftentimes patients, what they do is they take it for a month, 2 months, and then they abandon it. And that causes the evolution of the drug-resistant strain. And what they have found, what they now do is, this is called as direct observational direct observation therapy. This is something what they are now doing in some of those African nations where it is very endemic. A healthcare provider will come to you at a specific time, and they will ensure that you are taking the medicine in front of them. Not that you will be taking the medicine at your wishful time. I believe they bring in the medicine, they make sure that you take the medication at a fixed time in their presence. You don't skip those drugs, okay? So that's what is called as DOT, or direct observational therapy for treatment of tuberculosis. And this is becoming a little bit more, it's giving kind of encouraging result. That way you know that the person is taking the drug not skipping or, it minimizes the development of the multi-drug resistant strain in the infected individuals. All right, folks? Now, the last one in this, what I want to talk about is, I say it's a re-emerging infectious disease. What is a re-emerging infectious disease?
Re-emerging infectious disease.
Re-emerging infectious disease. Some coming back again. These are some of the diseases which was a significant public health problem in the past, and their incidence have decreased over the last couple of, couple of decades. We have come down on the incidence, but now it is again, you see a spike in those incidents and those diseases, and it has become a major public health problem. So there were some of the diseases in the past, but over the decades, we have minimized it or lowered the incidence, but now lately we see an increased spike, or we see a spike in the incidence of those diseases. Such diseases are called as re-emerging infectious disease. There's a whole, when I teach we are not teaching now, for some time, infectious disease, there's half the time we talk about re-emerging and emerging infectious diseases with the bacteria, with the viruses, with some of the protozoans. Those are re-emerging. The Lyme disease is an emerging pathogen. So Zika virus we can call it as Ebola, and all those are emerging.
H1N1.
Huh? H. pylori is an emerging one. Tuberculosis is re-emerging. So is measles, pertussis, diphtheria, the whooping cough is a re-emerging pathogen because people don't want to vaccinate their children because there's some, things are going around that if you vaccinate, there's an increased incidence of autism, or you run the higher risk of autism. So parents don't vaccinate their children, and now we see an increased incidence of some of this whooping cough, pertussis, and all those. So, reemergence is partially due to an increased rate of HIV and AIDS patients. That epidemic of HIV and AIDS is partially to contribute for the tuberculosis because they get immunocompromised, and once you have immunocompromised situation, tuberculosis bacteria strikes you in the heart. Yet at the same time, aggravate the progression from the latent to active tuberculosis when you have a complicated immune deficiency, either due to viral or otherwise. Then you will transform from a latent tuberculosis to an active tuberculosis. Anti-tuberculosis drug, it slowed down the spread for some time. Not to mention that the drug resistance, as well as the multi-drug resistance form emerged due to the discontinuation of the anti-tuberculosis drug. You stop taking those drugs, some of the drug resistant strain evolve, and those drug resistant strain evolve. Once they evolve, they are also they can be also easily transmitted, so it goes in an explosive way, and the entire population of a major chunk of the population is infected. Worldwide incidence is still increasing, and as I mentioned earlier, it's the 6 million people that get tuberculosis infection every year. Possibly half of the people they're dying also, but you also have an increased newer patients which are being reported, to the health department. It's one of the disease that also need to be reported, and individuals who have an active tuberculosis, they are in the active database of the National Center for Disease Control, and the local public health department also have to notify it. There are certain diseases which you have to notify to the public health department, the local public health department. Tuberculosis is one. Got it? But there is also some discrepancy, if you get a norovirus infection, in where the elderly patients are kept, in one of those elderly care facility, you have to report to the public. But if you get a norovirus outbreak or what is commonly called as the stomach flu in one of the cruise line, then you don't. No, I'm telling the opposite. It's something like opposite. If you get in the cruise line, then you don't have to report it. But then if you get in the healthcare facility, you have to report it, or the other way around. In the healthcare facility, no, it's the other way around. That's why it gets all the way, like in the paper and all. Whenever there's a Norwegian cruise line, there's all virus, but nothing to do with Norwegian cruise line. Okay. It's the other way around. I think like if it is a cruise line, it has to be reported to the public health department, and that's why it gets explosive. But if it is in a healthcare facility, an elderly healthcare facility, then it needs not to be reported to the public. Okay. Alrighty, folks. So you had all a lot of fun, I believe, and I think you all got. Did I answer all your question? Okay. Any question? Yes.
Yeah. The one that I had asked earlier, like, why do they ask if you went to another country, if you got exposed to that? Like, why is it going out of this country that you're more likely to get exposed to tuberculosis?
Because it might be endemic in many areas of the world. It's pretty endemic. You go there, somebody like, they're not that well mannered. They will just cough on your face. Or sneeze on your face directly.
I did want to hear more about, it sounded like you were saying that a healthy individual could be exposed to TB but then not develop full-blown TB. Is that right, or did I misunderstand?
A healthy, immunocompetent individual may get the bacteria, but it may not be a full-blown disease because the immune system will keep a good tab on it.
So will they clear it without antibiotics, or?
Yeah, they will clear it. It depends upon the individual, and it depends upon the individual immune status as well as the fact that their lifestyle. Put it that way.
Okay.
Will they still test positive?
Huh?
Will they still test positive?
They will test positive. They might test positive because it depends on what you're looking for. If you're trying to look for the sputum, and then you will test positive that way.
But for instance, for PPD?
PPD, again, they will test positive because you have developed the antibodies.
So
You have developed antibodies, and you might develop the B-cell memory. Then you will test positive. But you will not be eternally, you will still be a healthy individual, and you won't have all the shortness of breath, fever, perspiration at night, or sweating, and all those things.
I know. And that beginning of the formation of the tumor that was in that first image, would that then recede and just go
Then
away?
over the course of time, yes, that will be.
Oh.
That will be.
Okay.
All right, folks, so now with all of this background, I don't intend to do anything.
We thought it was a rat.
Genome is, huh?
Me too.
We have 30 seconds to reorganize.
Let's finish up. It will be interesting.
We got 10 minutes. You'll love
Oh, yeah, 10 minutes, so much things can done in 10 minutes. Yeah, 15. Genome is the cell's genetic information, and it is mainly in biological world. The genome, whenever we talk about genome, we usually refer to the context of DNA. So the genome is mainly composed of DNA in biological world, except in a small group of viruses that have RNA genome, instead of DNA. So when we talk about genome, it is implied is that DNA is the genome, but there's an exception amongst a small group of viruses which are called as the RNA viruses. They have the RNA genome. Can you tell me a virus with an RNA genome? I'm sure you all know it. HIV. Can you tell me one more?
Hep C.
Hep C is the one, but also the one we'll be discussing in the lab, the influenza. Remember we talked about the RNA-dependent RNA polymerase. So that one is also have a RNA genome. So few of the viruses, there's a whole group of viruses that have an RNA genome, and it's just an evolutionary thing. They are equally successful as the DNA viruses, and their distribution is they're equally widely distributed like the DNA viruses. Okay, so the genome is, except in a small group of viruses that have the RNA genome, and such viral group have obviously the RNA. And then the other one is the chromosome. What is chromosome? Chromosomes are thread-like structure within the cell. Oftentimes people, laymen, they think that the DNA and the chromosome are the same, but there is a fine line of difference. Chromosomes are thread-like structures within the cell, and they are made up of the DNA and the associated proteins. Those proteins are the histone and the associated protein, which are basic histone and the non-histone protein. In the bacterial cell, these are absent in a bacterial cell. They're absent in the bacterial cells. But they are present within our cell. We have both the histone and the non-histone protein. That makes up a complete chromosome along with the DNA. In the bacterial cell, those basic histone proteins are absent, and that's one of the prime differences. Although when we're talking about the differences between the prokaryotes and the eukaryotes, I did not discuss this aspect. I was purposefully avoiding that time. A gene, if this is a DNA structure, if this is a double helix DNA structure, if this part of the DNA, if this segment of the DNA, it codes for a functional protein, then it is called as a gene. So it's called as a gene. It's a segment of gene that gene is a segment of the DNA that codes for a specific functional product. Is the unit of genome. Several genes will make up the genome component of the organism. So this piece of DNA, if this piece of DNA over here, if it codes for, say, cytochromes, if it codes for the cytochrome, then you say this is the genome of the cell. That's what you say is the genome of the cell, if it codes for the cytochrome. If this part of the DNA codes for a protein, if this segment of the DNA encodes for a protein with no function, with no known function, can we still call it as a gene? Can we still call it as a gene? No. Any part that it codes for a functional product is a gene. If this part of the DNA it codes for, say, transfer RNA. That's one of the product of the DNA transcription. Then this is referred as a gene. This is a gene. This is a gene. This is not a gene because it codes for a protein with no activity.
No function, not a gene.
Yeah. It has to be specific functional product.
Does the gene, like the box is around both strands of DNA?
Yeah.
So
The
it's
DNA,
both of them.
yes, both the strands are essential for the when it is to be transcribed to a functional. Now, gene expression and the central dogma. There is something what is called as a central dogma of molecular biology, and that says, or it defines that every time, whatever the genetic information you have, it is transferred from DNA to RNA to proteins. This unidirectional the unidirectional flow of information is what is called as the central dogma. This unidirectional flow, and when you go from DNA to RNA, this process is via the transcription, and from the RNA to the protein is the translation. So here you have the transcription process, you have the translation process, eventually you will get the protein. And this flow of genetic information, this unidirectional flow, is the central dogma of molecular biology. The unidirectional, so this is the unidirectional flow of the genetic information. The DNA to RNA and RNA to DNA, that is present in all members of the biological world, with the exception of a small group of viruses which are called as the retroviruses. So this unidirectional flow of genetic information from DNA to RNA and RNA to protein, that central dogma is conserved amongst all living organisms. All living organisms. Except a group of viruses which are grouped as retroviruses. They defy the central dogma.
But if they're, do they divide if they're not living?
Yeah, I'm talking about in all living organism, that central dogma it plays a role. It's only absent. It is exception is a group of viruses which are viruses. You know what? This is an ongoing debate. What do you classify viruses as? Living or non-living?
Non-living.
I would non-living. Because they aren't producing their own anything, they need something else to survive.
But then once it goes inside, it behaves like any intracellular parasites. Outside the host, they will behave as a non-living entity. But once it goes inside, it takes the host cell as a hostage. Okay? So inside the cell, it behaves like any of the living organisms, but outside, they behave like any inanimate objects. And that's why we are in a constant debate where to classify viruses as living or non-living. In this instance, the central dogma is defined by this group of viruses which are called as retroviruses. And the retroviruses includes both the DNA viruses as well as some of the RNA viruses. So so those retroviruses, it includes the DNA viruses, some DNA viruses, as well as the RNA viruses. RNA viruses, the classical example is the HIV. For the DNA virus, which belongs to the retrovirus, despite the fact it has a DNA genome, still it belongs to the retroviruses, are the hepatitis B virus. Hepatitis B virus. It belongs to the retrovirus family. And these retroviruses, they have this enzyme called as reverse transcriptase. They have this reverse transcriptase which alters the central dogma. It uses the RNA, and from the RNA it makes the DNA. So from the RNA, instead of going from RNA to protein, it goes one step backward. So here is the reverse transcriptase, it will make the DNA, and this DNA will again make RNA, and then the protein. Hepatitis B. What's it? Oh Lord.
Time to go.
Aren't you excited? Oh boy, you're opening a can of worms now. Other people will shoot me.
Really quick, did you say that the retroviruses include both, all of the DNA viruses?
Oh no, not the all. Retroviruses include some DNA viruses as well as the RNA viruses.
All of the RNA viruses?
No, not all. Some. Like HIV. Or some of the DNA viruses like the hepatitis B. Hepatitis B is again very unique in its own way. Alright?
Free. Ah, shit.